All right, so I just want to show how to, after these two videos, this is part three. I want to show um, how to run and all these examples that they are on GitHub. Just so some people that are starting and students get used to how to compile, how to do it fast. So this is GitHub, my paste bin. This is my repo I created. So you go to GitHub, HFTrader, and my paste bin. This is local. I have all the, some miscellaneous code I delete, I add, and usually use this place to exchange code. So you come here and clone or download, then use HTTPS is fine. Copy to clipboard. I'm using Linux, so what it does is I can go to this is my test folder. What I do, I just paste it here and do git clone, and that's it. Should be my paste bin folder created in there, and that's it. It's there. I don't usually, for small projects like this, I don't use CMake or anything like that. I just use the command line. It's fair and easy enough. So what you do is let's run the first one. You can go G++ or Slang plus compute how-to CPP. If you just do this, it's gonna create an A out. That's probably not what you want to do. So let's remove this guy and give it a proper name. Compute power 2, right? If let's have a look at the code, because I'm not sure. I usually don't remember things. Okay, so the parameter 10,000 is hard coded. So let's just run this thing. It's there. It produced the result. What we want to do now is let's just time this. Right? Time. Because printing out all this code is gonna take time as well, I don't want that. So let's just redirect this to dev null. Let's see. Okay, so this is 0.04. This 4 milliseconds is nothing. It's really pretty fast. Let's raise a little bit this number actually. Instead of let's put 100,000. Let's see how it goes. Usually I prefer just modify the code and create parameters, and yeah, it's just a mess to be doing. And time, alright, 160. Yeah, let's raise it a little bit. I think 500. Alright, now it's taking more time. Okay, 2.6 seconds. You should notice that we didn't do any optimization. Let's just put an optimization flag so the compiler generates faster code. Let's see. Alright, not much better. 464 milliseconds, which is good for 500,000. That's okay. Going back, we have what? Compute POW2. We have compute POW2 domain divide. Let's have a look and try to run this one. compute how to divide, domain divide. Alright, so this guy is there. It has a, let's put the same number. And this is 2 million, let's put 500. And here I put like this is 4 threads because this is a multi-threaded. So let's do the same. Compute how to domain divide, and let's put the same name. Go. What's wrong? Here, this file requires compile library support. Oh, standard C++ is the modern C++ crap. Alright, so standard C++ 11. I'm using it. I told you. I mean, I'm not against it. I use it all the time, but it's it has so much hype. So now what is that? It's missing p threads. LP thread. Interesting. C++, modern C++ is using p threads. Of course, std threads are just a thin wrapper around p threads. See how it does. Compute power 2, domain divide, go. Printed out a big number. We don't want that. We want the time. Adjust the time and print to def null. Which is interesting. So the real time, this is wall clock time, is less, is smaller. However, the user time, it's almost 3 times. Oh, that's because of all the 4 threads running at the same time. Well, you'll see that even at this this level, multi-threaded, it doesn't add so that much, because you spend so much time doing synchronization and doing contention, mitigation, that you just spend so much CPU time. When you put everything in one core, everything just goes so much faster. So that's why I'm really reluctant to use multi-threading if not necessary. It's usually it has not much gain. You know, for this 4 threads, of course, if you have a approach that you can use 1,000 threads, and then and on the right problems, then it's the right thing to do. Now, if you use 1,000 threads on a problem this size, on these specific problems, you are probably going to spend like a minute, 1,000 times more. If you use things like CUDA, for example, because CUDA, just passing a vector back and forth takes a huge amount of time. Latency to and from the device is huge. Alright, so let's just see. Capturing, it's fine. That's my command line for capturing the video. So what else? Compute domain divide. We saw that it's slightly faster. Let's look at the other ones. We have compute how to domain divide template. So we use templates now. That's my attempt to do it faster by because in the original, in the multi-threaded code, you see that if this block is head, then it does this. So there's a bunch of ifs. What I did in the other one is compute power domain divide template. Is I eliminated all these ifs by making this code template. It's templatized based on if the block is ahead or if it has a next block after it. Meaning that when it compiles, this if should go away and keep this branch if it's a head block, and otherwise delete this branch and keep this second branch as a for the rest of the blocks. Then here, what I do for depending on the position, I call the template that's specific for the case. This one is not a head block and does not have, meaning that this is the last block. This is the middle block because it is not a head, and it does have a next block. So this is the middle. Let's see. I mean, if all this template attempt works. So -03, the usual modern C++ thing for std threads. Let's see how it runs. Domain divide template. Oh. Yeah, this is 2 million. 2 million. Let's make it 500 like I did in the other one. My bad. We are not comparing apples to apples. So, yeah, I mean, it's slower. Twice slower. What I'm doing wrong? Is it because it is slower? Or is it because of cache? No? Looks like this is a failed attempt. Alright, that happens all the time. Usually when I develop something, I have very good ideas, I implement them, and they just don't work. Then I throw them away or keep for reference. I mean, sometimes it's good. You can get new ideas. Alright, so the fourth attempt is this multi-threaded x86, which means that instead of doing this is the same as the domain divide, but now I don't use 32-bit blocks anymore. I use 64-bit. The problem with this one, I mean, it should be faster because you are using the full power of a 64-bit CPU. However, come on, what's the name? Multi-threaded. Okay. So the problem with this is that I have to use assembly, because there is no way, there is no construct, there is no syntax in C++ that I can use to multiply two numbers and get the result and the carry. There's just not a way to do it. This when in G++ there are extensions that you can use using the int 128, but that is I found that they do some crazy stuff in there because they use a library, so every multiplication, every division, sum ends up in a call. And by starting in line like this, you can avoid doing that. So for the additions, I need one division and one addition. The division is I need to pass a uint64 and a carry. In this case, is the high, and a divisor, which is constant, and it generates a quotient and a remainder that then I use to propagate the calculation, the carry. The other one is just the addition. Once I have the carry, I just add to the new number, and it's here. That is it. Where is it? Oh yeah, so this is the main core. This is the sweep. So it goes and it computes the low and the high. So it makes a shift on the block by 64-bit. I take the low and the high part. Then I add the carry that is passed before. Then I make the division, and I have the new value and the carry that's going to be applied to the next loop. The problem with doing this division split like this is that when you do a 32-bit division or even a 64-bit division, what you get is the compiler avoids a div instruction because it's extremely slow. It can take up to 10 to 15 cycles according to the Intel manual, depending on the specific chip that you're using. But usually it's extremely very slow. What we do, but my hope here is that the blocks are so big and the gain is going to be so much better that the div instruction would not have much impact. What the compiler does is does a multiply and overflow. It's a technique that's well known. I can show you later. I think I'm gonna post a video later with the link. It's very cool, and it avoids to do when the divisor is a constant number, then it can compute a division in one cycle instead of 10 or 15 cycles using the div assembly instruction. Alright, so let's try to compile. Let's try now, let's do it. Let's just do this. Multi-threaded. Rookie mistake. Alright, so let's see how it behaves. Time. How to multi-thread. How many bits I'm computing? Oh, I need to, this one I did a command line. Okay, so the usage is number of bits and threads. 500,000 for threads. Let's see, 3 threads. Slower. I mean, it's still 0.578. That's not the fastest. I think the fastest is the 0.3. Yeah. So another not so great attempt. Okay, so what else we have? We have multi-threaded pipeline. Pipeline is a technique that we use in FPGA a lot when doing Verilog and when you have many calculations and in series, then you don't want to wait for the first calculation to end, to compute, to start a new one. So you break it up in phases, and you start by computing the first phase of the first calculation, then you move to the second phase at the same time that you are doing the first phase of the second calculation. So you end up, if you have 3 phases, you end up doing 3 calculations at the same time, which increases the area of the FPGA using, but it increases the throughput and increasing a little bit of latency as well. I try to do this. I mean, you have a look. It's not a big deal. The way I chose to synchronize them. It's kind of neat. It's a technique that uses even and odd atomic numbers, atomic sequential numbers. So blocks, they just wait for given sequence number to become even, and then they push, and the next box waits for being odd. It's a cool technique that I use a lot on, especially in financial markets. It's very useful. I will follow up with a video of an example of that in market data propagation, for example. Alright, so this is the pipeline. I just do the pipeline. Not the same mistake again. Alright, so I think this one, oh, it's hard coded. Let's put 500. Okay, let's compile it again. Oh wow, that's slow. And the reason that was not expected, but the reason for this is that it's so much contention. I'm managing contention block by block, and that's while in the other ones, the domain divide, I divide it in groups of blocks, and you only check for sequence numbers every, the n divided by the number of threads, so it's much less contention. This being dominated just by the multi-threaded code. Yeah, that's the worst one. This technique works pretty well in FPGAs though. It's because in FPGAs you pretty much don't have contention, you have control of the clock, and yeah, or you actually have explicit control of contention, while in C++ and you just you are open to these things because you don't have control over what the processor is doing. All right, I think that's it. That's what I tried to do. The best results were for the domain divide with 0.3 something seconds. Then the serial code. Then what came next? I think it was the multi-threaded x86, then the domain divide template, and worse was the pipeline. So you see that the serial code didn't go that bad. It's actually a very good solution. In many cases, it's a serial code well written. It beats most multi-threaded code, and that's I think I can do a video on that too. It's because of cache effects and how the processor optimizes serialized code, while multi-threaded code usually messes up with the CPU cache and makes things much slower.